Anybody have any homework questions? Yep.
On stresses in A,
Mm-hmm.
A, we wrote is the thickness of 0.001 meters on every side but the one shown.
Okay.
Hey, look at it. Yeah, this one we didn't know.
Oh yeah, so so if I exaggerate the wall thickness in this drawing, we have a thicker wall there, thinner everywhere else, and you're calculating the stress at two places. One's here and one's here. And so when you do this one, okay, so call that A and B. When you calculate the shear stress due to torsion at A, that's going to be negative T over 2 times 0.001, because that's the wall thickness there, A median. And when you calculate it at B, where that 0.001 is for A is going to be 0.003. So the stress is going to be a third as much. Is that all? The only question about that? Okay. Yeah, so the thickness, the place where you enter the thickness, that's referring to the wall thickness where you're calculating the stress. The lowercase t in that formula. Any other homework questions? Yeah.
What do you think about number 7? So it's the circle,
Yeah.
and then you say express these stress tensors in their computation maybe I was like you were helping me with it yesterday, and like there's something about like rotating it like 180 degrees. There's nothing in number 7 that says that. It's just like the stress tensors and then.
Oh, yeah, this one only has... oh, in the coordinate system shown, though.
Okay, so yeah, it's y-axis. You have the problem thing?
Yes. Okay, so, like, let me do G as an example. So this angle's 30 degrees. So when you use the formula to calculate the shear stress at the point G, your capital coordinate system is going to look like this. Your capital Z that way, your capital Y that way. And then in that capital coordinate system, your shear stress, your XY shear stress is going to be negative T rho over IP. And then you have to think about what rotation you need to do to go from this coordinate system back to the one that's drawn in the problem, which is this one. That is 150. So theta is equal to positive 150 about x. And so then you do so that's where you get your Q matrix, and then you go Q times this times Q transpose, and that gives you the stress tensor in the coordinate system as it's drawn. And then calculate the eigenvalues of, so that'll give you the true stress tensor. Then calculate the eigenvalues, that'll give you the principal stresses. And so if you get, so say you calculate the eigenvalue, and it gives you, we'll call it stress 1, stress 2, and stress 3. Okay, so it gives you those eigenvalues. Then your stress in the principal coordinate system is just sigma 1, sigma 2, whoops, sigma 3. And I think what you should get there, I mean, CF, so C, F, D, G, and E, the only difference between those is the rotation of the coordinate system relative to where they are. So your principal stresses will be the same for all of those. Then you'll get different ones for B, and for A you won't have any stress at all because the shear stress due to torsion depends on how far you are from the center, and that's at the center. So along the center line of a circular cross section, you never have any stress due to torsion, just like you don't have any stress due to bending moment along the neutral axis.
So like for C, if we had to rotate C's coordinate system, we wouldn't rotate it at all.
For C and B, you don't have to rotate it at all because the capital coordinate system is already the given one.
What did you just say about torsion? At the origin there is 0?
Yeah, right at the center of a circular cross section, there's never any stress due to torsion because your rho is always 0.
Oh, okay, yeah, makes sense.
Any other homework questions? We've been talking about stresses in beams. Now we're going to talk about macroscopic deformations of beams. You can think of it as sort of, you have stresses all along the beam. If you integrated those stresses, you'd end up with, think about it as the strains. So at every point along the beam, you have strain. And if you integrate those strains, you get, by the end of the beam, you have the beam is bent down 0.5 centimeter and it's 1/10 of a centimeter longer than it would have been, that kind of thing. So we're going to talk about how to do those calculations. So likely the last set of topics that we're going to do is macroscopic deformations, and statically indeterminate structures. Indeterminate structures. And this is all related to beams. Structures made out of beams, macroscopic deformations in beams. Macroscopic deformations has to do with, say that you have a beam like this, and you put a load on it there, and a torsion there, and a force there. Then that produces a deformation that in this case might look something like this. And you can think of there's going to be some angle change due to that downward force, and there's going to be some length change due to that tension, and there's also going to be some twisting of the beam due to the torsion. And so you could talk about what the displacement is of the end of the beam compared to its resting orientation. Any questions about that idea?
Are you saying that the picture like looks linear? That's why you drew a...
I'm saying that that's supposed to be like show you where the beam would have been before the deformation. So it's like its deflection is this much. And its elongation is this much. And we're going to use that idea in statically indeterminate structures. And here's the idea of statically indeterminate structures. Based on the rules of statics, we can solve this. We've done some of these kind of problems. Say you have two members connected by a pin joint, and they're also connected to the ground by pin joints. And there's a force here, you know. We know how to solve a problem like that. But if I make some simple changes to this, we can't solve it if it looks like this. I'll just make one change to this. So that's still a pin joint. These are still connected by pin joints. But now this beam is a fixed joint down here. Okay, and say we still have that 1,000 Newton force. Okay, so no matter how good you are at statics, there's just no way to solve this. That's what statically indeterminate means. You don't have enough equations to solve for all the variables. But that's kind of unsatisfying to not be able to solve that, because you can easily imagine putting this structure together, and it's hard to believe that that the loading wouldn't be consistent, the deformation wouldn't be consistent from one time to another. It looks like a perfectly reasonable thing to put together. So we should be able to solve for those reaction loads. And the way that we do it, so to solve it, we need extra equations that come from the deformation of the materials. And when I say deformation of materials, we're talking about those macroscopic deformations. And the way it works is whatever deformation happens with these beams due to the reaction loads that are actually occurring, we know that the horizontal member and the vertical member still have to meet at a single point. That point might be moved, but that joint requires that those points, you can think of those two members agreeing about where that point is. And this member also has to, the vertical member still has to be connected to the ground at this point, and it has to be vertical at that point. It can be bent after that point. But so those requirements for how these materials are going to deform give us extra equations that we can use then to figure out what the loads are. Okay. We couldn't do that in statics because we didn't have a way to calculate these macroscopic deformations, how they relate to the loads, but now we're going to be able to. And so that's why these macroscopic deformations and statically indeterminate systems are sort of, it's all one thing, you know, because you use one to solve the other one. Okay, so the first thing, part one of this section, is the macroscopic deformations of beams. And we're going to deal with the following deformations. So this is going to be broken up into first elongation. And that's due to, first, pretty predictably, that's one way to have elongation in a beam is tension, compression. You know, if you have tension in the beam elongates a little bit. If you have compression in the beam, it shortens a little bit. And then there's another one that maybe you talked about a little in Physics 1. You can also have elongation in a beam or shortening in a beam due to temperature change. So we'll start with that. Then second, we'll talk about angle of twist. So, and what causes angle of twist? What causes a beam to twist about its axis?
Oh, torsion.
Torsion. Yes, thank you. No thanks to the rest of you. And then the last one is deflection. And you could think of that as due to shear forces or bending moments, but we know that those kind of go hand in hand. They have that derivative integral relationship with each other. So we're going to calculate this based on bending moments. And before we can calculate these, we have to calculate the internal loads in the beam because this torsion and this tension and this bending moment are the internal, you know, the things that we already know how to calculate. These are the internal loads. So in doing these kind of problems, we're first going to calculate the internal loads, then we're going to use those internal loads to calculate the tension, the elongation, the angle of twist, and the deflection. And then how do we combine these things? How would you guess? Yep, exactly. Again, the fact that we're talking about relatively small deformations sort of comes to our rescue, and we can calculate these, each one of these, as if it's the only thing going on, and then just add those results together at the end. So if you have a beam with complicated loading, you first calculate the elongation, then you calculate the angle of twist, then you calculate the deflection. You just add all those results together, and that tells you how the whole beam is deformed. Okay, so the first part is elongation. Due to tension and compression or a temperature change. And I'm going to start with tension compression. Okay, so say that you have a beam like this, and it's in tension in some way, and we're going to use the same coordinate system we've always used for beams with the x-axis along the long axis. The stress at a single point, and so let's choose a single location to investigate. Okay, so I'm going to choose this. It doesn't look infinitesimal, but imagine that's an infinitesimal disk with a thickness that's equal to dx. Well, the stress at that point, it's an XX stress. This is at the infinitesimal disk. Is equal to the internal tension at that point divided by the cross-sectional area. And then if we wanted to calculate the deformation along the x-axis of that disk, the strain at that disk, EXX, is equal to sigma XX over E, which is T over EA. And then to find the total macroscopic deformation of the beam, well, let's think of, so let's keep going sort of in pieces. So then the elongation along the x-axis of the disk, I think that should be with a C. Okay, so what we're talking about here is starting with a disk like this. After the deformation, this disk has elongated to this. And then this difference in the length in the x direction is what I'm going to call du. Yes?
What is the E again? In the strain?
That is Young's modulus, so that depends on the material. So for a given internal load, if the material is really flimsy, you're going to get a bigger strain. If the material is really stiff, you're going to get a smaller strain. And that's going to translate to how much this disk stretches in the x direction. And you can calculate this as, so this infinitesimal change in length along the x-axis is equal to that internal tension times dx divided by EA. So just going step by step, we got the stress, we got the strain, we used the strain to represent an infinitesimal displacement, and now we just have to integrate it. So then the total elongation another way to think of this, in other words, the displacement of the right end of the beam U is equal to the integral of T dx over EA, integrating from 0 to the length of the beam. Okay, so this is the integral definition of elongation due to tension.
Integrated from which to which there? O to L? What's O again? Or
0. That's 0 to L. Yeah, just from one end to the other, the whole length of the beam. We're just going to, if you think of this beam as being made up of a whole bunch of these infinitesimal disks, we're just adding up the elongation for each one of these disks to get a total. Okay, so that's the integral definition, but like with most of these integral definitions, most of the time we're not going to have to use the integral. We're going to do it as a sum of like a, we're going to usually be dealing with problems where you have a finite number of pieces with constant internal tension in between those pieces. So if the internal tension as a function of x is constant along the length, or piecewise constant, then we get these simpler formulas. The first one is if it's constant along the whole length, then the displacement is equal to TL over EA. If it's piecewise constant, on n intervals, so say this beam is broken up into n intervals. Each one of those intervals has a constant internal tension. Then U for the whole beam is equal to the sum over all of those n intervals of t, and any one of these things can change, so I'm going to write this as ti li over e, well, we're not going to change materials, I suppose you could, ei ai. So these are the three formulas that you're going to need for elongation due to tension. I have sort of an intuition question. All of this, like we kind of went through the whole derivation of this. It's not very long, but we started out by calculating the stresses at individual points and then worked from there, right? But through this whole class, we've been aware of the fact that, like, look at the way I drew this beam. We had point loads acting at these two, at the left and right endpoint. And in this whole class, we've been talking about how you can't trust the stress values at those two ends. So how does that come into this? I mean, this whole derivation, I mean, if we're adding up the deformations over the whole beam, then we have to be adding it up at the ends, and we don't trust the stress values at the ends. So is that a problem? It's not really a problem. Anybody have a feel for why that is? Well, percentage-wise, at the two endpoints, we don't trust, those results are not going to be good. Near the two endpoints, we're not going to get good results for the deformation of the left end or the right end. But since we're assuming that the beam is much longer than these excluded regions, these bad regions are, these bad deformations that we calculate at the ends are going to be swamped by the good deformations in the middle. And so even though we're adding in two regions where results aren't good, overall our results are going to be good anyways. Sort of understand what I mean? So what about St. Venant's principle and not trusting the ends? That's kind of the answer. It'll be all right.
It's kind of like putting, take a good beer and then put 2 drops of water in it. That's your bad ends. You'll never notice.
Yeah, that's exactly right. Yes. I'm going to use that next semester.
Very well. Or, sort of proper fluid.
Yeah, right. Yeah, people who don't drink beer are like, I don't get it! I only drink lighter fluid. This approach also works for non-prismatic beams. As long as the cross-section doesn't change very fast. So as long as the cross-section changes gradually, and so if you think of a beam where the cross-section is changing, as long as this angle, you can think of that angle as representing how quickly it's changing. So these are both theta. You can use this for theta less than about 10 degrees, which is actually quite a bit. But if it's more than that, then the assumptions that we're using to come up with our formula for the stress at points inside this beam, those assumptions aren't going to be valid anymore.
Does that mean that 10 degrees is the maximum that we can assume that the beam is going to go back to its original state without.
Nope, that's not why. It's that if you have a beam like this, you know, here's one end and here's the other, you're going to get stresses that aren't just axial stresses in this beam when you put it into tension. This assumption that that the only significant stress is going to be an XX stress, that's not valid anymore, and that's going to mess up the results. So you just don't want it to be, so this is bad, this one's, the one on top is okay. If you have something like this, we're just sort of out of luck in calculating the elongation. Yep?
Is that kind of like certain parts of that one like will deform more?
Will be what? Will deform more?
Yeah, like the smaller ones or something?
So in that case, it's not just that, because if that was all it was, you could use the integral definition, represent that change in A as a, so you'd have to deal with that anyways. Like in this case, you'd still have to represent that cross-sectional area as a function of x, you know? But then you could use that integral formula to do the calculation. But this one, the problem is deeper than that. The problem is that what we assume is a reasonable way to calculate the stress tensor is not reasonable anymore for something that's changing its cross-section this fast. Any other questions? Okay, well, let's do, that's really all we need for this. So let's do an example. So let's say that there's a bar connected to the ground. There's a 10,000 Newton force at the top. There's a 3,000 Newton force at the middle. This is 2 meters long. And let's say over the whole thing, the area is 0.01 meters squared. And it's made out of steel, so E is 200 times 10 to the 9. Poisson's ratio isn't going to come into it. I'll leave that out. And we want to calculate the elongation neglecting the weight. The weight's going to have a tiny contribution to this stress. Okay, so the first thing we have to do is calculate the internal loads. Well, we just have to calculate the internal tension so far. So first step is calculate the internal tension T is a function of x. So let's draw it like this, the way we're used to. So let's say this is the 10,000. And then at the midpoint, we have the 3,000 going this way. And then at the right, we have some tension, I don't know, I'll call it Rx. You know, we have this reaction force that keeps it from moving. And if we're just trying to calculate the internal loads, we can skip what's happening at the right endpoint. If I had flipped it the other way and worked from the ground, then we would have had to calculate that. So what's n? How many points do we have where the subfunctions could change?
3.
Yeah, n is equal to 3, so we're going to have to do 2 cuts. Cut 1 is from the left end to the midpoint, so that's 0 to 1. So we have the 10,000 Newton force at the left end. We haven't made it to the 3,000 yet, so all we have besides that is just the internal force T. And normally we would put in the shear force and the bending moment and the torque and everything, but we're only dealing with the tension in this problem, so this is all I'm going to write. So Newton's second law says 10,000 0 plus T0 is equal to 0, and so for that first cut, T is equal to negative 10,000. So is the first piece in tension or compression? It's in compression, which means that over that first half of the beam, we're going to expect it to get shorter. And now cut 2. This is valid for x from 1 to 2. We have the 10,000 at the left. Then we have the 3,000 pointing to the left in the middle. And then we have our internal T. So Newton's second law says 10,000 0 plus negative 3,000 0 plus T0 is equal to 0. And so T is equal to negative 7,000. Okay, so the second half, is that tension or compression? Compression. So the second half is also going to shorten, and so the whole thing is going to shorten. And we're going to figure out how much by just calculating the shortening in the first half, calculate the shortening in the second half, and just add those two results together. Yes?
But is it possible to get compression in the first half and tension in the second half?
Yes, it is. If this 3,000 had been 20,000, we would have had an internal tension of negative 10,000 on the first half, and on the second half we would have had an internal tension of 10,000. So yeah, it is. All right, so now the elongation. I wrote it before as a displacement. I'm probably a lot of times going to write it as a delta, like a change in length. But anyways, it's equal to T1 times the length of 1 over EA plus T2 times the length of 2 over EA. T1 was negative 10,000. The length was 1 of that first region. E is 200 times 10 to the 9. A was 0.01. So that's the shortening in the first piece. And in the second piece, it's negative 7,000 times 1 meter, because 1 meter is also the length of the second half, divided by 200 times 10 to the 9 times 0.01. And you get a total value of negative 8.3 times 10 to the minus 6 meters. So it shortens. That's what that negative sign tells you. A total of 8.5 microns.
Can you use upside down triangle or delta so then people don't get confused?
No, I will not do that. Any other questions? Okay, let's do one more example. So let's say we have a beam that's cross-section is changing slowly. The length of the beam is 0.5 meter. There's a 20,000 Newton force on that side and a 20,000 Newton force on this side. At the left end, let's say we have a square cross-section where the lengths of the side are 1 centimeter. And at the right side, we have a square cross-section where the lengths of the side are 6 centimeters. And we want to know what's the elongation. So what we have to do, this is changing steadily as x changes. So there's no way to break this up into a sum of constant values. So instead, we're going to have to represent the area as a function of x and then integrate. So since the area varies steadily with x, we're going to have to find a function a of x and use the integral definition. Of delta. All right. Well, if we think of the side length, let's plot side length first as a function of x. It starts out with a value of 1 centimeter, and then at an x value of 0.5 meters, it has a value of 6 centimeters. So let's come up with a function for that line. So you can think of that as like y. It's also equal to the length of the side. It's a line, so it's equal to mx plus b. When x is equal to 0, what's what's b? What's the length? So what's the y-intercept of this function?
Say again, please.
Okay, so we're so this is what the length of one of those sides does as x changes. Okay, and we're just trying to come up with a function for that length, and then we can just square that function to get the area. Rise over run. That's so m is rise over run. So the rise is 0.05 over a run of 0.5. So that's 0.1. So m is equal to rise over run, which is 0.05 divided by 0.5, which is 0.1. And then we need the y-intercept.
0.01.
Yep, 0.01. And so this function, the length of the side as a function of x, is equal to 0.1 x plus 0.01. The area is just equal to the side length squared so that's 0.1x plus 0.01 squared and if you pull out some numbers, you end up with 0.1 plus x squared over 100. Okay, that's one of a million ways you could write that function. But that's the area of this shape as a function of x. We also, I didn't do this, but you need to check that this meets that 10-degree requirement. You can do that with what? Inverse tangent. So 0.05, the inverse tangent of 0.05 divided by 0.5, that's going to be way less than 10 degrees. So this is fine. It doesn't look like it the way I have it drawn here, but that's a small angle. So now we have a function for the area. We have to figure out the internal tension. Can you just look at this and tell me what the internal tension is going to be? If you can't, that's fine. You just need to do the cuts. It's going to, the magnitude is 20, and it's in compression, so it's going to be negative 20. Okay? So cut 1, blah, blah, blah. We get that T is equal to negative 20,000 over the whole beam. So the elongation is equal to the integral from 0 to 0.5 of negative 20,000 dx divided by the Young's modulus, 200 times 10 to the 9, and then also divided by that area function, which is 0.1 plus x squared with 100 in the numerator now. You can pull all the constants out, and you get negative 1.0 times 10 to the minus fifth. That's the constant that you pull out, times the integral from 0 to 0.5 of dx over 0.1 plus x squared. How do we integrate that? Yeah, just use substitution will work fine. So if u is equal to 0.1 plus x, du dx is equal to 1. So dx is equal to du. And you have negative 1 times 10 to the minus 5, that's still the same constant, times the integral. Okay, I have to change the boundaries of integration. So when x is equal to 0, u is equal to 0.1. And when x is equal to 0.5, u is equal to 0.6. And now we have du. I'm going to write it as u to the minus 2 du. And so that's equal to the constant times negative u to the minus 1 integrated from 0.1 to 0.6, or evaluated from 0.1 to 0.6. And you get 8.3 repeating times 10 to the minus 5 meters. Any questions about that? Okay, let's take a 10-minute break. Come back at 2:13, and I'll do thermal expansion. I didn't write down the negative sign. This answer should have been negative, so you might want to get that in your notes. The example I just did should have been, the answer should have been negative 8.3 repeating times 10 to the minus 5. I guess before I do thermal expansion, let me do one more example. So I just want to show, like, we're used to doing, with internal loads, we do cuts where the loads change. But when we're using these sum formulas for the total elongation, we have to consider, you know, there's 4 things that go into that piecewise constant formula. There's the internal tension, the length, the length doesn't count for this, but the Young's modulus and the area. And if any one of those things changes, you need to make that a new piece. You know what I mean? So let me do that. So let's say that we have a beam connected to the wall. So it has a bigger cross-sectional area piece and a shorter one. And let's say this length is 0.4 meters. This is 0.3 meters. And if this is piece 1 and this is piece 2, the area, the cross-sectional area of piece 1 is 0.01 meters squared. The cross-sectional area of piece 2 is 0.003 meters squared. And let's say we have, at the shoulder here, we have a force of 5,000 newtons. And then at the end, we have a force in the same direction of 8,000 newtons. And we want to calculate the elongation. We need to know the material too. So what's elongation? So say that the Young's modulus is 110 times 10 to the 9th. I forget what metal that is, but that's some kind of metal, copper or something. Okay, well, the first thing we have to do is calculate the internal loads, and that means we have to calculate that external load at the wall. So if I do a free body diagram of the whole thing, we have a force here that we don't know yet. I'll call that R. Then we have this horizontal force of 5,000 and another horizontal force of 8,000. Newton's second law says R0 plus 5,000 0 plus 8,000 0 is equal to 0. So R is equal to negative 13,000. What's n? How many places where the subfunctions change? 3. So we're going to need 2 cuts. So cut 1 is for x values between 0 and 0.4. It's going from the wall to the shoulder. We have a force going this way of 13,000. We have a known force of 5,000 there. No, we don't. We haven't gotten there yet, so all we have left is this tension T. So Newton's second law says negative 13,000 0 plus T0 is equal to zeros. So T is positive 13,000. And then cut 2 is valid for x values between 0.4 and 0.7. On this piece, we have the 13,000 Newton force going to the left. We have the 5,000 Newton force going to the right. And then we have the internal tension. So negative 13,000 0 plus 5,000 0 plus T0 is equal to zeros. And so T is equal to positive 8,000. Any questions about the internal loads? All right, so now the total elongation is the elongation for piece 1 plus the elongation for piece 2. For piece 1, we have a tension of 13,000, a length of 0.4, Young's modulus of 110 times 10 to the 9, and then a cross-sectional area of 0.01. for piece 2, we have an internal tension of positive 8,000, a length of 0.3, Young's modulus of 110 times 10 to the 9, and a cross-sectional area of 0.003. And if you add those two up, you get a total elongation of 1.2 times 10 to the minus 5 meters. It's positive, so it elongates. Any questions about that?
Can you scroll up, please, real quick, sir?
Tell me when to stop. Or should I just do this?
Oh, yeah.
Does that help?
Well, your example and your free body diagram, your 5,000 newtons, that flip.
Oh, on the top and bottom?
Yes, sir.
Okay, so we're treating it like no matter, remember, like we're sort of thinking of it always as being a distributed load anyways, so it doesn't even matter where it's applied.
Okay. Good.
Yeah. Any other questions? Okay, so now let's talk about, what did I call this one? A, I think. I have this whole like outline structure of this because we have main topics and subtopics and subtopic A and B and stuff. So this is elongation topic B, right? Temperature change. So this is elongation due to temperature change. Also known as thermal expansion. And the deal with thermal expansion is you get every kind of normal strain in every direction positive normal strains that go along with increases in temperature. If the temperature goes up, everything gets bigger. So the strain due to temperature is equal to a constant times the change in temperature. This constant is called the coefficient of thermal expansion. And just like Young's modulus, you can Google that and it'll tell you the values for whatever kind of engineering material you want. It has units of 1 over degrees Celsius. And if you go through the same thought process that we did for expansion due to internal tension, you get that the elongation of a material due to temperature change is equal to the coefficient of thermal expansion times the length times the change in temperature. And this is the one we're going to use. It says heated up, the size increases. That's true of all solids. It's true of most liquids, not water. If you cool it down, the size gets smaller. Size decreases. Okay, so the way to interpret this is no matter what kind of length measurement you take, you can take any length measurement of any material. If you take that measurement and then increase the temperature, and then take the same measurement again, you'll get a bigger value if the temperature goes up. Okay, so think about like a donut, a torus. Don't think about an actual donut. I'm not sure if this really works with donuts, but think about like a steel torus. If it looks like this at the initial temperature, and then you increase the temperature, what happens to the whole of the torus?
You shrink.
That is what half of the people seem to think is going to happen. And in a way, I mean, I can understand that thought process. But the fact is, this is a measurement that you could take before.
Yep.
And so if you took that measurement again after increasing the temperature, it'll get bigger. It makes sense if you think about it as, like, think about the material that surrounds the hole.
Is that true for all the material?
That's true for every material, yeah.
You will get bigger with heat?
Yep.
Makes sense. So if you heated this up, this is going to get longer. If
Right.
you just wrapped it around,
Yeah.
that's going to get longer. So it's
And if it gets longer, the circumference gets longer, it means the radius has to get bigger, yeah. And that's why, this is why engines don't run very well cold, like the pistons in your engine aren't designed to be optimally efficient at 0 degrees or whatever. And so things don't run great until the engine gets up to the temperature that it's designed to run at, because everything is just a smaller size than it's supposed to be. All right, so let's do an example. So let's say, well, let's do the same example we just did. Okay, so we have this thing. With a length of 0.4 meters on the left half and a length of 0.3 meters on the right half. And we have a force here of 13,000 and a force here of 5,000. Is that what it was? And a force here of 8,000. So say that in addition to these loads being applied, the temperature increases 100 degrees Celsius. What's the elongation compared to unloaded and at the original temperature? Well, the total elongation is going to be equal to the elongation due to internal tension plus the elongation due to the temperature change. In the last example, we calculated the elongation due to tension. So we found that the elongation due to tension was 1.2 times 10 to the minus 5 meters. And now let's think about what happens due to the temperature change. So the elongation due to temperature, oh, I need to give some material stuff. I was supposed to give this when I started this problem, so let's pretend I did that. So alpha for this material is 1.0 times 10 to the minus 5, 1 over degrees Celsius. I guess that's all I missed. And again, that's something you can just look up, like Wikipedia has a list of tons of materials, gives you those values. So the elongation due to the temperature change is the coefficient times the length. And for the temperature change, we don't have to break it up into pieces or anything unless you have pieces that have different coefficients of thermal expansion. So this is just 0.7 times the change in temperature. Positive means the temperature is increasing. Negative means it's decreasing. So for us, this is a positive 100. And we get an elongation of 7.0 times 10 to the minus 4 meters. So the total elongation is 1.2 times 10 to the minus 5 plus 7.0 times 10 to the minus 4. And so you get 6, no, you add them. So that's 7.12 times 10 to the minus 4 meters. Any questions about that one? Yeah.
I have a question about the thermal expansion coefficient. Why isn't it directly proportional to degrees Celsius?
It is.
But then, like, if C gets higher, then the elongation would get, or that coefficient would be smaller.
It's not the. It doesn't matter what the. It doesn't matter what the temperature is. It just matters what the increase is. So this says that it raises. This doesn't say that it's at 100 degrees. You know, it says that it increases 100 degrees. Is that what you mean?
No, like the actual alpha sign.
Mm-hmm. Why isn't it just a?
He doesn't realize the units are canceling.
-5, 1 over degrees Celsius.
Oh yeah. So the units have to cancel so that. Because yeah, so that in the end you get something in meters. Okay, well, let's see. Any other questions? So let's see how this works in a simple statically indeterminate system. So let's say you have a bar that's connected to the floor and the ceiling. It's 1 meter long. That's a pretty short room. It's like that room in Being John Malkovich. That's a movie that old people used to watch. Ask your grandma about it. She thought it was great. The cross-sectional area is 0.01 meters squared. And at the midpoint, let's say there's a force of 20,000 newtons pointing toward the floor. What are the reactions? What are the reaction forces at the top and the bottom? Well, how do you know it's statically indeterminate? The first step is always to go through the statics and see what you have. Maybe it looks statically indeterminate, but you can solve it. So, and we're going to need those equations anyways. So, first do the statics. A free body diagram of this bar. Let's say that we have our bottom and then our top. I'm not even trying to guess the directions of these things. I'm just putting them in the positive y direction. The signs will work out on their own. And then we have a 20,000 Newton force at the middle. And so Newton's second law, just y components, says RB plus RT minus 20,000 is equal to 0. So we get this equation that says RB plus RT is equal to 20,000. And that's the only useful thing we can get out of the statics. And now you can see that this is statically indeterminate because we can't solve this system based on what we can get from the statics. We have two variables in one equation. And so now we're going to use, so it's statically indeterminate because it's two variables and one equation. So now we're going to figure out what we know, what we can do based on the way this thing's going to deform. Since it's connected to the floor and the ceiling, we know that it can't change its length at all, okay, if it's attached. So to use the elongation, notice that the length can't change. Because the attachments at the floor and ceiling prevent that. Okay, well, let's go into the internal loads. I'm going to tip it over sideways because that's how we're used to dealing with it. So let's say we have our RB here, our 20,000 pointing to the left, and RT on the right end. How many places are there where the subfunctions can change? 3. So we're going to do 2 cuts. cut 1 is to the midpoint, so x is between 0 and 0.5. We have RB that way, and then we have the internal tension. So Newton's second law, I'll just use the x components, says RB plus T is equal to 0. So T is equal to negative RB. And then I'll do cut 2. X is valid between 0.5 and 1. This time we're including RB at the left, and now we have that 20,000 Newton force pointing to the left, and then our internal tension T. The x component of Newton's second law says RB minus 20,000 plus T equals 0. So T is equal to 20,000 minus RB. And now we know that our elongation, our total elongation, is equal to the elongation for piece 1 plus the elongation for piece 2. And so the expression for the elongation for piece 1, it's going to be T times the length over EA. T for piece 1 we got from that first cut is equal to negative RB. Who's still with me? Okay. So we have negative RB times the length of that first piece, which is 0.5, times E. I didn't give an E. It turns out it'll cancel out in this problem. I did give an A. It turns out that would cancel out too. Let's just write it as EA. And the elongation for the second piece is 20,000 minus RB times 0.5 divided by EA. And what we know, because of the attachment to the floor and the ceiling, is that these have to be equal to 0. And so we get this second equation that says, if I multiply this stuff out, we have negative 0.5 RB plus 10,000 minus 0.5 RB is equal to 0. I multiplied both sides by EA. That disappeared. And so we have RB is equal to 10,000. Now, how do we know what RA is? We have half done. What's RA? How do we get that? Yeah, go back to the statics equation. So plug this back into the statics equation. and you get, we know that RB plus RT is equal to 20,000. So 10,000 plus RT is equal to 20,000. So RT is equal to 10,000.
So you got half done what's RT, not RA?
What?
You got RA in there.
Where?
Half done what's RA.
Oh, RT is what we want.
Okay.
There was never any RA.
That secretary wrote terrible.
Yeah, it's crazy how she moves my hand even while I'm up here lecturing. Okay, well that's not a, so maybe I should have done a cooler example where that force wasn't at the midpoint, because then we would have gotten different answers for RB and RT. But still, we had a problem that we couldn't do based on the statics, and we used the way that the material deforms to figure out how the load was distributed between the two reactions. And that's the idea of statically indeterminate. Any questions? Okay.
So when we're, oh, sorry.
Yes.
I didn't know that I asked a question. So there was a pin and there was a rigid connection on the bottom. So that is basically this example.
Yeah, it was two rigid attachments, but I just, and
Because if there was a pin up there, it would have been like a...
it would have been the same thing. I mean, I skipped X components and Y components for things just because there was only stuff going on in one direction.
Just like that once we do Y or anyone.
Yeah, that's right. That's exactly right, yeah. We, like, if you really treated it carefully like a fixed joint, you would have put in the couple and all the, and then at the end it would have just been a lot of zeros and we would have been left with this.